The fifth one, a ramp function. A ramp function is given by f of t equals to t. Graphically, it is represented like this. T is 0, f of t is 0, t is 1, then f of t is 1. This is a ramp function. Now, the applying the Laplace transforms, it is f of s equals to Laplace transform of f of t, that equals to integral 0 to infinity e to the power of minus st of t dt. Integration by parts gives us that f of s equals to minus t e power minus st by s 0 to infinity plus integral 0 to infinity 1 by s e to the power of minus st dt. When you substitute the infinity here, the e power minus st term will become 0, then this term will become 0. When you substitute 0 here, then t term will become 0 and this whole term will become 0. Then the remaining term is this, then 1 by s integral e power minus st, which we are going to get e power minus st by s. It is nothing but e power minus st by s square between the limits 0 and infinity. Then f of s for ramp function you are going to get as 1 by s square. The sixth one, parabolic function. The parabolic function being is given by that f of t equals to t square, graphically represented this with t and f of t. Then for 0 it's 0 square, 0, 1, 1, and 2 it's 4, right? See, increasing. Applying Laplace transform, that is f of s equals to Laplace transform of f of t, that equals to integral 0 to infinity t square e power minus st dt. This can be solved by using the formula that integral u dv equals to uv minus integral v du. Let us assume u equals to t square and dv equals to e power minus st dt. Du equals to 2 times t to the power of 2 minus 1 dt. Integrating this value, then you will be getting v equals to integrate this e power minus st by s of minus. Now substitute this in this formula. This value is equals to u, that is t square, and v minus e power minus st by s between the limits 0 and infinity minus integral of v is this, minus e power minus st by s, and du is nothing but 2t d. Now if you substitute these limits, this will be a 0 value. So minus of minus, you'll be getting plus 2 divided by s integral e power minus st of t dt. We have already found the Laplace transform of this value in the ramp function. We got 1 by s square. Now you can substitute that directly here. So f of s here is given by, for the parabolic function, 2 by s multiplied by 1 by s square. That equals to 2 by s cube. Next, seventh, Laplace transform of t to the power of n. From the definition of the Laplace transform, f of s equals to integral 0 to infinity t power n e power minus st dt. This is again integral u dv, that equals to uv minus integral into du. Now let u equals to t power n, then du equals to n t power n minus 1 of dt, and dv equals to e power minus st dt, from which integrate on both sides you will be getting v equals to 1 by s minus e power minus st. F of s equals to, we can write this, t power n by v, that is s, this is negative, e power minus st between 0 and infinity minus integral v is 1 by s minus e power minus st, minus minus will be getting positive, and t power n minus 1 dt. We all know that this term will become equals to 0. Then f of s equals to 0 plus n divided by s integral e power minus st t power n minus 1 dt. This equals to n by s Laplace transform of t power n minus 1 equals to n by s of n minus 1 by s and n minus 2 by s and so on, 3 by 2, 2 by 5, 1 by 5, Laplace transform of t power 0. However, Laplace transform of t power 0 equals to 1 by s, as it is 1, which is unit step input for that Laplace transform is 1 by s. Laplace transform of t power 1 or t, then it is a ramp, that is 1 by s square, and Laplace transform of t square, which is nothing but the parabolic, that is we got as 2 by s cube. By generalizing this, we can write that Laplace transform of t power n is equals to the n factorial divided by s to the power of n plus 1. The eighth one, unit impulse function. Unit impulse function is given by that delta t equals to limit delta t tends to 0 u of t minus delta t divided by delta t, which is obviously a derivative of unit step function, that is delta t equals to d by dt of u of t. For delta t has the value 0 for t is greater than 0 and infinity at t equals to 0. However, infinity value at t equals to 0 is unreal. Let us now introduce a new function, that is g of t equals to 1 minus e to the power of minus at. It may be observed that g of t could approach delta t provided a is alone very large. Again, g dash of t is given by d by dt of g of t, that equals to a e power minus at. Integral 0 to omega g dash of t dt is given by 0 to omega a e power minus at, which equals to 1. If we apply the Laplace transform directly, that is f of delta is given by Laplace transform of delta of t is equals to limit a tends to omega Laplace transform of g dash of t is equals to limit a tends to infinity Laplace transform of a e power minus at, which equals to limit a tends to infinity a divided by s plus a, which is nothing but infinity divided by s plus infinity, which is again infinity. Infinity divided by infinity, we are going to get 1. This gives that Laplace transform of an unit impulse function is unity.